review. Right now we're doing 2012 BC pre-response 6. It is a BC only question because it involves things like Taylor and Maclaurin and ratio test and all that awesome sauce stuff. All right, so we are given a Maclaurin series for G, and it's that thing that you can see in front of you right there. So part A, using the ratio test, determine the interval of convergence for the Maclaurin series of G. Okay, so so that's all they want us to do, right? Okay, so the ratio test, right? So when you do the ratio test, right, the ratio test is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, right? And what we want to do is we want to set that whole thing less than 1, right? But before I bother to do that less than 1, I'm going to go ahead and set up my ratio. So the limit as n approaches infinity of, so a sub n plus 1 is going to mean take this nth term, right, and plug in n plus 1. So negative 1 to the n plus 1, although that's really not going to matter much to me, an x to the 2, and then in parentheses n plus 1 plus a 1 over a 2 in parentheses n plus 1 plus 3. So that's my n plus 1th term, right? And that's going to be on top of, and then I'm just going to copy the term here. So the reason I was kind of dismissive about the negative 1 to the n plus 1 is it's not going to end up mattering because since the whole thing's inside an absolute value, what's going to end up happening is that negative 1's going to be gone anyway. So I set up my ratio. So it's worth noting that just having this ratio set up is one of the points on your AP Calc test. Every single time, if it's a ratio test problem, set up the ratio of a sub n plus 1 over a sub n and get your free point. Later on, you're going to have to actually find it as a limit, right? So like evaluating the limit, that's going to be another point. So let's talk for a second about how this stuff shakes down. When I clean up my limit, and we're going to see if I can squeeze stuff in here and you can still see it, I have this limit as n approaches infinity. Okay, so the negative 1 to the n plus 1 is going to end up on top of the negative 1 to the n, which we'll deal with in a sec, right? And really it doesn't matter. It's going to end up being a negative 1 and cancel out. This is an x to the 2n plus 2 plus 1, so I'm going to get x to the 2n plus 3, right? And it's going to end up being over an x to the 2n plus 1, right? And then what's going to happen is, so everybody on the top, like notice that these guys stay on the floor they're on, right? So this guy was on the top floor, he stays on the top floor. This guy was on the top floor, he stays on the top. This guy was on the bottom, he's going to land on the bottom, right? So he's going to end up being a 2n plus 2 plus 3, so 2n plus 5, right? So these guys were the original fraction, right? These guys. And then these guys, right? So these guys, since they're the divisor, they're all going to get flipped. So these guys were on the now they're on the bottom, right? And then sure enough, on top of my fraction is going to end up being this 2n plus 3, right? And I kind of squeeze it in. I'm going to inch it over so you can see it. Cool. Okay, so let's loop down for a sec, and I guess I'll try and do it over here so you can see a little bit more, right? So I put them in the pairs that I put them in for a reason, right? These guys, right, these guys together, they just net a negative 1, which is going to end up being irrelevant anyway because it's inside the absolute value. So these guys technically net a negative 1. I'll give you that. That's fine. Okay. These guys, right, these guys right here, if you subtract the exponents, as you would when you divide, you're going to end up getting an x squared. Great. And if you leave these guys as they are, we'll deal with them in a sec. So I'm going to leave, this is an 2n plus 3 over a 2n plus 5. Okay, cool. So the first thing I want you to notice is that the only guys left that have any n's, this is the limit as n does something, and this is the only thing left with any n's. Meaning this limit only really pertains to these guys now, right? So I can basically go ahead and say, oh, I get it. This limit is what this thing is doing as n approaches infinity. These guys don't have any n's. There are no n's, right? This limit pertains to these guys. Well, because these guys have the same degree, they both have a degree of 1, I'm looking at their leading coefficients to see what they do. This approaches a 2 over 2 for huge values of n. So this bad boy is just a 1, right? Once I realize that, what I've got here is that this whole thing is actually a negative 1 times an x squared inside an absolute value. But again, the negative 1 isn't really relevant because that's the same as an absolute value of negative 1 times the absolute value of x squared. That's how multiplication works in an absolute value. And this guy is just going to be positive anyway. So after all that work, I end up getting that the absolute value of x squared is less than 1. So what's going to happen when I solve this is I essentially get that the two possible endpoints for this thing, right? The two possible endpoints when I solve, so the easy way to solve this is honestly to pretend that this says equal to 1, right? So pretend it says x squared rather equals 1. You would get x equals plus or minus the square root of 1, so x is plus or minus 1. So the bounds of your interval, right? So the interval, right? So the window we're looking at is from -1 to 1, right? Because if you picture numbers for x squared less than 1, 0 is obviously less than 1 when you square it. Anything 1 or whatever is, like anything bigger than 1 or equal to 1 is not. So that's great. This is the open interval, right? So this is the open interval. But that's not where our job ends, right? So far, in this fairly lengthy part A, we got 1 point for setting up the ratio. We get 1 point for evaluating the limit, which really, when you come down to it, is this step in red, right? I evaluated what happens as I approach infinity, right? I then get 1 point, right? So far I had 1 point for this, 1 point for this, and then I get 1 point for identifying this open window, okay? But now we have to actually find the interval of convergence, which means we test the two endpoints. So I'm going to erase all of this crazy amount of ratio stuff, okay? And now we're going to test the endpoints. So I now know that I need to test the endpoints of my interval. So I'm going to test x is -1, and I'm going to see what this function becomes if I plug in x is -1. So if x were a -1, this would be from n is 0 to infinity of a -1 to the n, right? And a -1 to the 2n plus 1 over 2n plus 3, right? So here's the thing. 2n plus 1 is code for an odd number, right? This is always going to be odd. The reason it's always going to be odd is because 2n is always an even number. So what that's basically saying is this whole thing is just a -1. It's a -1 literally all the time, right? So I'm pretty sure what's going to end up happening is I get an alternating series. This is essentially, from n is 0 to infinity, a -1 to the n plus 1 over a 2n plus 3. And you can check by plugging in some numbers. If you plug in n is 0, you're going to get a -1 on the top and a 3 on the bottom, right? And then if you plug in n is 1, you're going to get a plus, because it'll end up being a -1 squared, 1 over a 5, right? And then if you plug in the next value for n, which would be n is 2, you're going to get a negative, and you're going to get a 7 on the bottom, and so on, right? So this is an alternating series, right? So this is an alternating series that by the alternating series test will converge, right? It's an alternating series. The limit of each one of these terms as n goes to infinity is 0, right? And the terms are decreasing in value, right? You can look and see that as you look at these terms, they are getting to be smaller and smaller numbers, right? So the absolute value of the terms is decreasing in value. So once you know all those things, this thing converges. So right away, I know that x equals -1 converges, right? Now I'm going to do the same test, right? So I just have half of it now. I'm going to do the same test at x equals 1, and I'm basically going to get the same answer very quickly. So when I plug this in, I get -1 to the n. Over a 1, I don't really care that it had a power on it because it's a regular 1, right? 1 to any power, it's just a 1, over a 2n plus 3. And I'm basically going to get this exact same series that I just wrote, except with the opposite signs. The first term will be the 1 over 3, but it'll be a positive instead of a negative. The second term will be the -1/5. The third term will be a positive 1/7, and so on. By the exact same rules that said this one converged, this also converges. So x equals 1 also converges. What that means is that my answer to this entire question, right? So my final answer to this question is -1 is less than or equal to x is less than or equal to 1, if you want to write it that way. Or if you're somebody like me that really likes parenthetical notation, you could write bracket -1 to 1 bracket, right? And that's my preference because, I don't know, I dig me some parenthetical notation. This was actually a 5-point part A, which is pretty epic for a ratio test question, but it is what it is. So remember, you got 3 points earlier. The 4th point was for considering the endpoints. Even if you biffed it at the end and made a mistake, you considered both endpoints. That's point number 4. And then point number 5 was for getting the correct answer after considering the endpoints. Cool. All right, that was A. That was a very long part A. Let's go on to part B. So we already have 5 of our 9 AP points on that question alone, that one part A. Okay, part B. The Maclaurin series for G, evaluated at 1/2, is an alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2 using the first two non-zero terms of the series is 17 over 120. Show that this approximation differs from G of 1/2 by less than 200. This is asking you to use the next term in the sequence. So this is talking about the error for an alternating series, and the way we find the error is by using the next non-zero term. So what they told us to do is they had us approximate using the first two terms. Let me double check that I'm not speaking wrong. The first two non-zero terms. So what they had us do in part B is they had us use x over 3 minus x cubed over 5 to approximate, that's not how you spell approximate, to approximate G of 1/2. And when you do so, you apparently got 17 over 120, which is fine, great, cool. They gave that to us. They want us to show that the actual value of G of 120, right? So to approximate G of 1/2, my bad, is 17 over 120, right? That's the approximate value. They want us to show that the actual value, right? So the actual value, which is G of 1/2, right? Minus the approximate value, which is the 17 over 120, they want us to show that it is smaller than 1 over 200. Well, the trick is that what you want to do in order to show what the error, the max value of the error, is you want to max out the next term, right? This is the next term in the series, right? So you want to max out. So what I know for a fact, so I know that this thing, G of 1/2 minus 17 over 120, is less than or equal to, and then I'm going to max out the next term on the window from the center, which is 0 because it's a Maclaurin series, to the value I used, which is 1/2. Well, if I max that out, the only thing I can max out is x to the 5th. The bottom's a 7. So the max value of x to the 5th on this window is going to be the largest possible x I can plug in, which is going to be a 1/2 to the 5th over 7. If I clean that up, that's a 1 over a 32 times a 7, which is a 1 over 224. So I know the piece of information that's in blue, but I also know that because this value is a 224 on the bottom, it must be smaller than a 1 over 200 because bigger denominator means smaller fraction. So 224 being the bigger denominator compared to the 200, 1 over 224 has to be smaller than 1 over 200. So sure enough, that shows me that my value is less than 1 over 200. So in order to get your 2 points here, point number 1 was that you knew to use this term. Even if you did something wrong, you used the x to the 5th over 7 in some way, right? And point number 2 was that you actually finished it out and simplified this to show it was smaller than this. Cool. Let's do C. So that gives us 2 points left for C. Write the first 3 non-zero terms and the general term for the Maclaurin series for G prime. So now what they want you to do is they want you to derive G, right? So we know that G, right? We know that G of x can be written as x over 3 minus x cubed over 5 plus x to the 5th over 7 plus dot, 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 all the way down till you get to the nth term, x to the 2n plus 1 over 2n plus 3 all times that negative 1 to the n plus dot, dot, dot. So to find G prime, right, what I'm going to do to find my G prime is I'm just going to derive. So G prime of x should be, well, when I derive this guy, I get a 1/3. When I derive this guy, I get a negative 3/5 x squared. When I derive this guy, I get a 5/7 x to the 4th. And be careful, watch out for the instructions. They said the first 3 non-zero terms, which I did, 1, 2, 3, and the general term. So now when I derive this guy, remember that the only variable here, right, the only variable here is this x to the 2n plus 1. Everything else is a coefficient. So I'm going to get this negative 1 to the n, right? I'm going to drop the power down in front, so that'll be a 2n plus 1. X to the, I lower the power by 1, which would make it a 2n, all over this 2n plus 3. Because again, the negative 1 and the 2n plus 3, they were not variables, right? They're constants, they are coefficients, so they sit in front, and I just drop this power down. And that's my answer. So it was worth 1 point for the first 3 terms and 1 point for the general term. Notice that I put an ellipsis at the end because if this is actually equal to this series, it has to be an infinite series.